the slope of a secant line passing through 2 points on a graph of a function represent? One more time. The rate, it represents, but I don't have enough room. I write big. So the rate of change of y with respect to x between
Points.
those 2 points, of course. The rate of change of the function, or y, if you want to write for y, the function. Because y is the same with f of x. So one more time, what does it represent? The rate of change of the function, like its distance, with respect to x, like its time, between those 2 points. The average velocity, if you want, between those 2 points. Is that clear? Okay. Why is the slope important and what is it used for?
So represents the rate of change. Well, are we talking about instantaneous or?
Not yet. Why is the above slope? What is number from number 1? Why is the slope important? Why would I ever care about the slope of the line that goes through 2 points of a function? Why would I ever care?
You can use that to estimate or to guess the instantaneous velocity.
The rate of change of at any point. That's a good point. And also, I'm interested to know, and I can look at a function and see, first of all, the slope can be positive for you, positive, right? The slope, the line can look like this or can look like this. So first of all, it's good to know whether the slope is positive, which means that something is increasing, or if the slope is negative, it means that something is decreasing, whatever it is. So that rate of change, right? So it's either positive, the function is increasing, or the rate of change is negative, or the function is decreasing. So first of all, increasing, decreasing situation. Number 2, perfect. It will help us eventually find the rate of change of a function at an instant, not between 2 points, but at an instant. Like I'm driving to New York and you call me and say, look at your speedometer, tell me now what is your speed, and that will be the instantaneous velocity. Okay, so let's write it down. Why is this important? First of all, increasing, decreasing, because situation for the function. So if it's positive or if it's negative. If it's positive, the function is increasing between those points on average or decreasing. It helps in estimating the instantaneous rate of change. It helps us determine or estimate the instantaneous rate of change. How? By moving that point Q as close as possible to P. And I will be able to find an estimate for the rate of change of that function at that instant, which otherwise I wouldn't be able to because I don't have 2 points. Good. And what is it used for? It helps in estimating the, okay. Why am I interested to find the slope of the tangent line to the graph of a function? So forget about the secant line now. Why am I interested in finding the slope of the tangent line at a particular point?
Not instantaneous rate of change.
Exactly. To find the instantaneous rate of change. At that point, in other words. And now, how do I determine the slope of the tangent line to the graph of a function? Couple of steps. 1, what do I find first? of a
Secant.
secant line. Slope of a secant line. Which one in particular that works for any function? And we reviewed it and reviewed it and reviewed it 90% of the class last time. It's called? Exactly. Which equals?
Y equal, or M equals
Yes, okay, very good. That's fine. We can write it M.
half of X plus H minus half of X over H.
So this is the first step towards finding the instantaneous velocity or the slope of the tangent line to the graph of a function at a particular point. Then 2, after I find this, what mechanism do I use? If you can say, I have 2 here, and I'm going to determine the slope of the tangent line between 2.1 and 2. Then I'm going to get even closer, 2.05 and 2. Then I'm going to get even closer, 2.01 and 2. And then even closer, 2.001 and 2. Or you can say, by making what? What is this distance that I'm talking about? From 2, say it, not yet. I'm getting to that. You're ahead of me, which is very good. Exactly. Age approach 0. Not this. Careful. Not age equals 0. You cannot say age equals 0. You can say age approaching 0. Because as you know, we cannot plug in 2. We cannot say that age is 0, because if age is 0, then I have to plug in 2, and I cannot plug in 2 in this. Or I cannot plug age is equal 0 in this, because the denominator will be 0, and I'll get an error. So you can never, ever say age equals 0. You can say age approaching 0, or approaches 0. Good. Perfect. So this is basically what we discussed last time. Any questions on this? Any questions on this? And I have just a 5-minute quiz for you. Open notes, open book. Just not look to your colleague. 2 minutes. So finally simplify the difference quotient for this function. 1 minute. Okay. Thank you. Okay. Any questions for me before we continue? Yes.
Can you go over one of those again, the square root?
Yeah. You mean the one that we just had? The quiz?
Oh, yes, it is.
So
My notes was-
f of x plus h minus f of x divided by h, and this is the difference quotient. We cannot forget that. Oh. Thank you. And in this case, this is the square root of 2x plus 2h minus 5 minus the square root of 2x minus 5 divided by h. So now I have to multiply actually by, if this is minus, I have to multiply by the plus.
Mixed up, I'm sorry. The 2x plus 2h, where's the 2h coming from?
Okay. So when I replace x by x plus h, I have 2x times 2h minus 5. So if I have minus, the conjugate of that is the plus. So 2x plus 2h minus 5 and plus 2x minus 5. Remember, the key is to redo your notes more than once. Watch the tape if you want to. I think it's useful. Print out my notes if you want to. I can give them to you after I shred them now because I don't need them anymore. So if you want to print them or not print them, but save them somewhere on a flash drive so you can go back to them when you watch the video again. So now when I multiply a minus b by a plus b, I get a squared minus b squared, which is 2x plus 2h minus 5 minus 2x minus 5 divided by h, and I cannot miss this. This does not go away. The denominator cannot go away. The only thing that eventually will go away is this. That's what I expect it to go away. So then I simplify, and I see the terms with no h must go away. Then I have 2h over h and whatever I have in parentheses. Now I simplify, and I get that as the final. Square root of 2x plus 2h minus 5, the square root of 2x minus 5, and the square root of 2x plus 2h minus 5 plus the square root of 2x minus 5. So once we're doing class of 1, 2, 3 problems, you should expect something similar and you should have no difficulties with it anymore. Okay? Did you turn in your quiz or not?
That was his.
It was his, okay. Very good. Any questions? So you help me, I can post this because I was going to post it anyway and I had to write it, so Good? Good. Anything else? Other questions for me before we continue? On my agenda for tonight, I have a few things before we look at 2.2 and 2.3. And one thing is that I didn't get the chance to look at last time was actually two things. Number one, study the sign of an expression. Very important to be able to study the sign of an expression. And the other one, how to graph a piecewise defined function. And then we'll look at the next two sections, 2.2 and 2.3. Okay, ready? So number one, the first thing that I'd like to discuss is how to study the sign of an algebraic expression or function. Let's suppose we have a function and give me a rational function. Let's say that's not rational with a square root. You said square root. That's not a rational function.
Oh, yeah.
That's okay. So let's say we have this. And x in front. Assuming I have this rational expression, it has how many factors? How many factors do I see here? Four factors. 1, 2, 3, 4. And I have an inequality symbol, less than or equal to, and 0 on the other side. Okay. Now, what am I asked to find? So what is the question here? Well, I know I'm asked to solve. I'm asked to solve. But what am I really asked to find? I'm asked to, in plain English, find x such that this x plus 1, negative x plus 3 over x, negative x plus 4 has what sign? Of course. Because only negative is less than or equal to 0. I have to disregard the positive, right? Positive is not less than or equal to 0. So I am trying to find x values that make this expression to be negative. I recommend the following chart. Of course, you can use the method you like. You told me one more time that in this expression, there are how many factors? 4 factors. Each factor has to be on a line. So I have x plus 1. I have negative x plus 3. I have x. I have negative x plus 4. And I have the ratio, the whole thing. X plus 1, negative x plus 3 over x and negative x plus 4. Now, I would like to get what it's called the zeros of each factor. So now I'm going to ask you, where is x plus 1 0? When x is negative 1. Where is negative x plus 3 0? When x is? Where is x 0? When x is 0. And where is negative x plus 4 0? 4. Okay, so they have to be in ascending order. So from negative infinity to infinity, I will put these 4 numbers in ascending order. Which one will be first? And the next? Perfect. And then 3 and 4. Perfect. Now, x plus 1 is 0 under what? I know it's silly, but I just under negative 1. Negative x plus 3 is 0 under x is 0 under, and negative x plus 4 is 0 under 4. Now, what happens to the fraction itself under -1? Yes, because the top is 0. What happens to the fraction itself under 0? No, does not exist. Because the denominator is 0, I don't have a number. Perfect. What happens under 3? Excellent. What happens under 4?
No.
Because -x plus 4 is in the denominator. Perfect. Now, can you tell me x plus 1, -x plus 3, x and -x plus 4, what type of functions are these? If I ask you graph x plus 1, how would you graph it? As a parabola? As a circle? A line. Perfect. What will be the slope of this line? Right. So it will look like this, or it will look like this. Slope is plus. So it comes from which types of numbers and goes to which types of numbers? Negative to positive. Now the next one. Does it look like this, or does it look like this? So it comes from which numbers and going to which numbers? What about x? Does it look like this, or does it look like this? So it looks like this. So it comes from negative numbers. It will cross somewhere where it's 0 and go to positive, correct? Last one. What do you mean by the slope is negative? Correct. Correct. So it looks like this.
Starts in positive, goes.
Excellent. Good. How many subintervals we see here? 1, 2, 3, 4, 5 subintervals. On the first subinterval, please count the negatives. Even number of negatives. What will be the sign? Perfect. Please count the negatives on the second interval. So what will be the sign? When I multiply them or divide them, doesn't matter. Count the number of negatives on the third subinterval. Count the number of negatives on the third, or the fourth. I think I meant the fourth. And on the last. Now, I can write the final answer. You already told me what I'm looking for. Which sign am I looking for? Is this expression ever negative? In how many places? 2. And what will x be? Union 3 to 4. Very good. So let's write the final solution. So x in the interval, -1, 0, union 3 to 4. Now I have to be careful. I need to use parentheses or brackets, but I cannot use a bracket where the expression is undefined. And I have to use a bracket when the expression is 0 because the symbol has the equal symbol. So where is the bracket? Where is the interval? The parenthesis. Because 0 is allowed, I have to close it. Because 0 is not allowed, I cannot close it. 3 is allowed, I have to close it. But 4 is definitely not allowed, I have to leave it open. This is the way we study the sign of any expression. What we are going to encounter throughout the semester will be more difficult than this. Why is this easier? Because it was already factored. I don't have to factor it, right? But what we are going to see will be more sophisticated, slightly more sophisticated, because we will have to factor those expressions, those functions, and then study their sign. Yes, you can study the sign with a graphing calculator. Sure, no worries there. So I don't have to use this chart. I can just create this line and punch in the expression, put the expression in the calculator and punch in -5, and I will get a positive number. Punch in -0.3 and I will in here and I'll get a negative number. Punch in 1 in here and I'll get positive. Punch in 3.2 here and I'll get negative, and punch in 10 here and I'll get positive. That's another way. It doesn't matter. I prefer this way because I will connect this chart with another chart that we will be using, but it's up to you. You don't have to use this method if you don't like it. Okay? You can just put this in a calculator and just punch in numbers between these two, between these two, between these two, between these two, between these two. The sign of that outcome will tell you the sign of the expression. Any questions? Was this problem clear? Yes? Okay. Number 2 that I would like to continue with is a graph, a piecewise defined function. So I'm going to make one up, or we can find one in the book. It doesn't matter. So if you want to choose from your book, can anyone remind us what does this mean? What is a piecewise defined function?
So it's not a continuous.
It can be continuous, though.
It can be continuous?
Yes. I found a function in your book. Problem 50. Oh, you can see. Problem 50 on page 108. This is what we call a piecewise defined function. A function that is defined in pieces. For x between ta 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 ta, it's this function. Between this and this is this function. Between this and this is another function. That's what is a piecewise defined function. That's how it looks like. So I'm going to copy that function. And it has 4 different branches. X for x less than 1. 3 for x equals 1. 2 minus x squared for x between 1 and 2. And x minus 3 for x greater than 2. This is a super important topic in this class. Being able to graph a piecewise defined function, and later on we'll have 2 different things to add to this. I don't want to bother you with them right now. So for now we want to graph this function. First thing that I need to determine is what? Absolutely. I can do anything. I can choose anything. I can plug in anything till I find its domain. So how do I find the domain of this function? By simply looking at this. This will tell me all these 4 pieces of information will give us the domain. So this means to the left of 1, like -infinity 1. This means x equals 1. This means between 1 and 2, like 1 and 2. And this means like 2 and infinity. So can anyone tell us the domain of this function by simply looking at 1, 2, 3, 4? Perfect, excellent. So -infinity to infinity, correct. Now, I will have to put in the chart these 2 values, 1 and 2. Other values as well, x values, but 1 and 2 have to be in the chart. Why would I have to put 1 and 2 in the chart? Mandatory. Why? Why 1 and 2 are so important? Yes.
And x is less than or equal to 2.
Because those values, something happens. The function changes from blah blah to blah blah. So that value must be important. right? It's like a threshold. Here is this, over there is something else. Good. So now one interval is to the left of 1 with a parenthesis. Bear with me, I'll explain why I'm using this method. 1, I can already put it in. When x is 1, y is 3. No doubt about it. On the other side, I have another parenthesis. Under 2, I have a bracket opening to the left and a parenthesis touching it, which I did not have here, touching it going the other way for 2. This is this. This is this. This parenthesis is here, and this parenthesis is here. Now I know that this is an overkill, but please bear with me. Can you please tell me which expression will I be using between negative infinity and 1? I just want to write it one more time here.
X less than less than 1
Just x.
on this side.
That's the expression. This
Oh.
is the condition.
Okay.
Now, for 1 equals 3, I'm done. Which expression will I be using for x values between 1 and 2? Excellent. And finally, between 2 and infinity? Excellent. Which means that the graph that I have between negative infinity and 1 will never extend beyond 1 to the right of 1. The graph that I will have between 1 and 2 cannot extend to the left of 1 or to the right of 2. It cannot. And obviously, the graph that I have between 2 and infinity cannot extend to the right, to your left of 2, correct? Good. So now for x, this is a linear function. Give me some values to the left of 1. Of course, we have to have 0. 0 has to be part of the chart, unless the function is undefined at 0, but it's not. The function is defined everywhere. Correct. When x is 0, I have to plug in 0, right? Oh, you want also negative 1. Correct. Negative 1, negative 1. Now, I will do something that you may say, wait a minute, you can do that. And I will have to agree with you. I will plug in 1 in x. And you should say no, right? I cannot plug in 1 in x because 1 is not in this interval. Bear with me. If I don't plug in 1, I will have to plug in 0.99999999999, and so on and so forth. I will plug in 1 and I'll leave it as an open point. Okay. On the other side, I have 2 minus x squared. This is a quadratic function. Does it have a maximum or does it have a minimum? The leading coefficient tells us it has a maximum. So I expect to graph something like this. Okay, perfect. Let's plug in 1, please. 2 minus 1. 1 squared is 1. 2 minus 1 is 1. Let's plug in 2. Negative 2. Sort of, I'm done with the middle part. I'll see in a minute if I need anything. Now let's move to the right-hand side. I know you're not going to let me plug in 2, but I'll have to. So when you plug in 2 in x minus 3, you will give me, good. So let's also plug in what key number I should.
3.
Yes, indeed. 3 minus 3 is good. We're ready to graph this function now. Please give me the first ordered pair. Please give me the second ordered pair. You may have said it, I didn't hear it. Perfect, excellent. Please give me the next ordered pair. We're not there yet.
Oh, so you want, oh, to jump to the interval or 1, 1.
1, thank you. Is this an open point or a full point? The parenthesis tells you whether it's a full point or an open point.
Okay.
Open point. Done with the left-hand side with x. We cannot extend it to the right. This is it. Now, please give me the next ordered pair.
1, 3.
Correct. Full point or open. Very good. Please give me the next ordered pair. Exactly. So it's still open, so I'm back here. Please give me the next ordered pair.
Two negatives.
Very good. Is this an open point or a full point? Perfect. Remember how what do we have to graph now? What type of graph? Parabola. Opening. Having a max or a min? Please give me the next ordered pair.
So 2, -1.
Open point or a full point? You cannot touch this. I'm a little bit too close. I have to correct that. I'm going to move that to a little bit to the right. Or just put an open in there. Okay. So 2, -1. Perfect. Then, next ordered pair. This is the graph of our f of x. One more time. This point does not touch the parabola, and it's an open point. Any questions?
How would we do this on a calculator?
First of all, even if I'll show you how to do it on the calculator, we can do it right now. But you will not be able to copy it from the graphing calculator, and the calculator will not give you the details that you see here.
Well, I just didn't know if there was a way.
The calculator will not show you the open point.
Okay.
The calculator will not show you this open point. So you still have to be able to do it by hand. But there is a way of graphing it with a graphing calculator, but then you still have to copy it onto the paper. And how will you do that if you don't know these open points? Because the calculator will not give that. It's not as sensitive. Any questions on piecewise defined function? Graphing it. Any questions?
Not yet.
I'm sure you've seen this before, sometime. Okay, would you like to choose another and work on it for a minute?
I can do it at home.
I'm sorry?
I can do it at home. If everybody else has got it, I can do it.
No, I'm totally lost.
Okay.
Okay.
Just because I've done it, when I did it in pre-calc, it was a totally different way, so.
You can use your way.
Okay.
I have no problem. But what happens generally, and I don't even want to say it, is students continue with this line over or this function to the right, and then they graph the whole parabola, and they extend the line, and that's a mess, and I can't give more than 0. So I don't know how you studied it, but if it works for you, please use that method. I'm fine with it.
Well, it actually didn't work.
Okay.
I was just,
So let's find another piecewise defined function, and if not, we can make one up. It doesn't matter, so let's make one up. So f of x, 3, if x is less than 1, 1 minus x, if 1 less than x less than or equal to 3. and x squared minus 9 for x greater than 3. I will have to put the equal symbol at 1. Well, I don't. Actually, I don't. I don't want to put it at all. Okay? Okay, 2 minutes. Okay, 3. If I may interrupt for 1 second and ask you, what is this graph? What does this graph represent? A piecewise defined function. Okay. What does this graph represent? So in calculus, you will find these functions every step of the way. Even in 2.6. I just flipped some pages. What about this? And this is in 2.6. What is this function? It's a piecewise defined function. As you see, the branches do not overlap. So what you see to the left-hand side of 0, it does not go to the right-hand side of 0. What you see to the left-hand side of 2 does not go to the right-hand side of 2, and so on and so forth. Do we need more time? Okay, so obviously the first branch can be rewritten as this. The middle branch can be written as this. And the last one as this. Based on what we see, what is the domain? And I wanted to ask you here, what is the range? And I forgot. So one more time, the domain, negative infinity to infinity. And what about the range? Absolutely. From the lowest to the largest. Yes, indeed. Indeed. Perfect. So now in this situation, what do we have as domain? Without, exactly, exactly. So 0, 1, and 3, negative infinity to infinity. Careful, this is what how will I represent that the function is undefined at 1. There is nothing there. So to the left of 1, parenthesis, to the right of 1, parenthesis, to the left of 3, bracket, to the right of 3, parenthesis. Now one more time, I know it's an overkill. Between this and this, what do I use? Between this and this, what do I use? Perfect. And between this and this? Excellent. Good. So to the left-hand side of 1, to the left-hand side of 1, all I have is to write 3. In between 1 and 3, when I plug in 1, what do I get? Perfect. When I plug in 3, what do I get? Perfect. Now on the other side, when I plug in 3, what do I get? Perfect. When I plug in 4, what do I get? Excellent. That's all I need. Keeping in mind that this is quadratic and these are linear. Can anyone give us the first ordered pair? Perfect. Next ordered pair. Perfect. And finally, what type? Perfect. Now 1, 0. What type? And 3, negative 2. Full or open? And it's a straight line. And now 3, 0, full or open? 4, 7. So this was 3, 4, 5, 7. However, this has to be a parabola. Does it open upward or downward? Does it have a minimum or a maximum? Minimum. So the minimum is right somewhere here at 0, negative 9. And that's our f of x. So the domain was negative infinity 1 union 1 infinity. What about the range?
-2.
Excellent. Negative 2 to infinity. Very good.
But not 0.
And not 0. Yes, thank you. Absolutely. Negative 2 to 0. Union 0 to infinity.
So what is that union? Does that just mean there's a...
Instead of writing together with at the union. The intersection is when they overlap and I look for the common territory. The union is a symbol that says, okay, it's here or here. In other words, the range has values here or here. Very good. Other questions here? Is this okay? Okay, perfect. So I think now we are finally ready to continue with 2.2, which is called the limit of a function. So that's my page 4. Now coming back to what we wrote sometime last Monday. This is what we wrote. So I said then that, and I'm going to copy this because I like to have it here. So we said then that the slope of the secant line PQ does not equal, but gets closer to the slope of the tangent line at P when age approaches. Does not equal to. This is what we wrote last Monday. Yes, we remember that? Remember we had this graph, we had the slope of the secant line PQ, and this was our Q1, then Q2, then Q3, and we determined the slopes of all these secant lines. And this was the distance called h. So as we move Q closer and closer to P, h approaches 0, it gets closer and closer to 0. Therefore, the slope of this line will get, as we move Q closer and closer to P, the slope of this line will get closer and closer to the slope, not equal to, but closer and closer to the slope of the tangent line at P, which basically means as h gets closer and closer to 0, this line becomes the tangent line. We agreed on that last time, correct? Okay. Now, this is not the mathematical way of writing it. How are we going to write it? Instead of writing this or presenting an arrow saying gets closer and closer, I'm going to put the equal symbol. I'm going to say the slope of the tangent line at P. And I'm going to use an operator called LIM. LIM stands for limit. The limit of the slope of the secant line PQ will equal the slope of the tangent at P when h does what? Does not equal to, but approaches 0. So this is the mathematical symbol or mathematical way of writing this box that I had last time, which I couldn't use. Then I couldn't use the limit operator. So the limit of the slope of the secant line, the limit which is determined when h approaches 0, will be the slope of the tangent line at P. Now this is in general for the slope. Now, whenever we try to determine a limit of a function, this is also a function. We created it last time. We put it in the calculator even. It was a limit of a function. We created it, right? But when we write the limit of a function as x approaches a is L, so this is one step further from this, not further, but more sophisticated. This is just an example of what we did last time. But in general, in the general case, this is what we write. And now I'm going to write this in words. Limit of f of x as x approaches a is L. We don't know what this means yet. It means a lot. But for now, we're just looking at it, and we just want to understand how to read it first. Limit of f of x as x approaches a from either side, or from either side. I'm inserting it in here. From either side is L. We still don't know what it means. There are two other limits as well, and then I'll explain what it means. There is a limit from one side, which is from the left, and there is a limit from the right. So one more time. Limit of f of x as x approaches a from either side is L. Okay, here's another one. Limit of f of x as x approaches a, and it's like an exponent but just minus, which means with values smaller than a. So to the left of a would mean, if a is 2, to the left of a would mean 1.9 or 1.99 or 1.99999 like we used last time is L. So this is the left hand limit. We have also the other one. How do you think we're going to write it? With a plus as an exponent for a. It looks like an exponent. And this will be the right hand limit. Okay, we know how to read this. It looks sophisticated. It's not. So limit of f of x as x approaches a from the left, or limit of f of x as x approaches a from the right is L. What is L? Okay, first of all, we have to write that down. Note, L must be a number, comma, not infinity. Infinity is not a number. If I cannot say that the limit is 3 or 15 or 1/3, and I say to you, it's approximately something, I could even say it's pi. I can say the limit is pi. It's acceptable. But if I cannot give you that number, then the limit does not exist. Okay. Another note. A function does not have to exist at a point for its limit to exist. So a function may have a limit, although it's on at a point, left or right, or either side, but it doesn't have to be defined there. Okay, I'll give examples in a minute. So first of all, we know how to read this. We know that there are three possibilities: limit from either side, limit from the left, limit from the right. We know that L must be a number. It cannot be infinity or negative infinity. And we know that a function does not have to be defined at the point for the limit to exist. Okay, so now let's analyze what this means. And I'm going to show you a few graphs, and then we'll look in the book at a few graphs. So here's one graph. Here's another. Okay, so we have 4 graphs. We're looking at 4 different graphs. Okay, this is A. And I'm going to say that this is 2. And I want to identify whether this function has a limit as x approaches a from either side. So the question is, limit of f of x, they're all f of x, f, of f of x as x approaches a from either side, does this exist or not? In other words, the concept of the limit means this. Where do the function values go? If from both sides they tend to approach the same number, then the limit from the left and the limit from the right are identical. They both exist. So then the limit from either side is that number that the function approaches, even if the function is not defined at that point. I don't care, because I cannot make x equals 2, right? It's x approaches a, I meant to say. X approaches a is not equal to a. So I don't care what happens at that point. So as long as the function values get closer and closer, closer and closer to the same number, the limit exists and is, in this case, what? Yes, it exists and it's 2. Because the function approaches 2 from the left and approaches 2 from the right. The other way around. 2 from the right and 2 from the left. So the limit exists and it's 2. Now I'm going to ask you for the same graph. What about the limit as x approaches a from the left of f of x? How much is it? 2. How much is the limit as x approaches a from the right? That's the reason why the limit from either side exists, and it's 2. I want to jump to this. This is my a now. And I'm asking you, limit as x approaches a from the left of f of x, and limit as x approaches a from the right of f of x. And then I'm going to ask you from either side. So from the left, what will you say? Follow my pen. Follow my pen. As x approaches a, the function values get closer and closer, closer and closer to So now as x approaches a from the right, as x approaches a from the right gets closer and closer to a, the function values approach infinity. So then the limit from either side of f of x will be, does the limit exist? Don't answer. Just read this note one more time. Does the limit exist? No. It's infinity. It tells me how it does not exist. But in parentheses, and we don't have to write this, but I will put it, it still does. It still does not exist. It's not a number. Okay, but I cannot write D and E. We normally write D and E, but not for this situation. For this situation is infinity. What will I have for this situation? From your left to negative infinity, from your right to, but from either side, I cannot write infinity, I cannot write negative infinity, I have to write D and E. This is the only situation in which I write D and E. Although this one is D and E as well, because it's not a number. Okay, moving on to this. So this is my A. And I have here 3, and I have here 7. So I'm asking you, limit as x approaches a from the right of f of x. What will you say? From the left. From the right. From both sides. From either side. Now I have to write D and E. Finally, This is my a, and let's say this is my 2. Limit from the left. Limit from the right.
2, 2,
Limit from either side.
2.
Exactly. We don't care what happens at a. We only care that both sides approach 2. The function doesn't have to be defined because I can never make x equals 2, as we know from before, from Monday, that we can never make h equals 0. I cannot make q into p. I can bring q as close as possible to p, but I cannot make it p. Okay, so I think we should look at a couple of graphs in your book, and then look at other examples. Okay. Why not? So let's start with problem 6, because I like this graph. So let's look at problem 6. For the function h whose graph is given, state the value of each quantity if it exists. If it does not exist, explain why. So it's problem 6 on page 96. 6 on page 96. First question. Find the limit of the function as x approaches -3 from the left. -3 from the left. Here's -3. And here's -3 from the left. And by the way, what type of function is this? Of course. There is no escape. So what is the limit of this function when x approaches -3 from the left? +4. 1, 2, 3, 4. +4. Please write it down. Limit as x approaches f of x. Limit of f of x as x approaches -3 from the left is +4. So here's how we write it. So this is problem 6 on page 96. Limit, part A, x approaches -3 from the left of f of x is +4. And what page? On page 6. Is that clear? Okay, part B. Limit of, it's not f, it's h. I'm sorry. Doesn't matter. Okay, part B. Limit of f of h of x when x approaches -3 from the right. Still 4. Perfect. -3 from either side. Still 4. So if you want to write it down, please do so. So limit as x approaches -3 from the right of h of x is 4. Since both sides are the same, therefore limit of h of x as x approaches -3 from either side is 4. Part D. H of -3 does not exist. H of -3 does not exist. This is an open point, and at x equals -3, there is no full point anywhere. Limit of h of x as x approaches 0 from the left. 0 from the left. So 0 from the left is 1. Then 0 from the right. 0 from the right. As x approaches 0 from the right, the function values get closer and closer to -1. As x approaches 0 from either side, does not exist. H of 0, +1, indeed, where the full point is. H of 0 is 1. limit of h of x as x approaches 2 from either side. 2 from the left, 2 from the right, from either side. So this is 0, this is 1, this is 2. Perfect. H of 2 does not exist, undefined. H of 2 is undefined. Limit of h of x as x approaches 5 from the right. Five from the right. 5 from the right. 3. Perfect. 5 from the left. 5 from the left. Let's talk about this. This is an oscillating type of limit on the left, type of function on the left-hand side. In other words, it's this at one point, and it is this, and then it's this, and then it's this, and then it's this, and this, and this. And it continues like this constantly, indefinitely. So the left-hand side is dne. It does not approach a particular number. It jumps all the time. Okay?
So long as the function between that is defined, right? Or
What do you mean by function in between?
between the interval.
It's a cosine function of like 1 over x. It will oscillate constantly. It will not approach any number. From -1 to positive, from +1 to -1, let's say, as an example, and it will continue like this forever. From the left-hand side, it will not approach a number. It will oscillate constantly. So I will write limit as h of x as x approaches 5 from the left is dne. From the right-hand side, it's very clear. It approaches 3, but from the left, no. Okay, let's look at one more. Let's say problem 9. For the function f whose graph is shown, state the following. Limit of f of x as x approaches -7 from either side. -7 from either side. Negative infinity. For part A, negative infinity. For part B, -3 from either side. Positive infinity. Very good. 0 from either side. Positive infinity. 6 from the left. Negative infinity. 6 from the right. Very good. And if I want 6 from either side, what will you say? dne. Now, I'd like to add what a vertical asymptote is. Let's talk about vertical asymptotes. Here's a graph. I'm going to say that this is a line that I call x equals 2. And this is a function. This is what we know from calculus, from pre-calculus, I meant to say. But now we can write it with calculus. If limit, like in this situation, as x approaches 2 from the left of f of x, or limit as x approaches 2 from the right of f of x, or limit as x approaches 2 from either side of f of x, is what? We conclude that x equals 2 is a vertical asymptote. What is the limit from the left of 2 for this function that I just drew? From the left. From the left of 2, infinity. From the right of 2. Oops. I meant from the right of 2, negative infinity. What about from either side? Right. So, in short, if the limit from the left or the limit from the right, or both, are infinities or does DNE, then x equals 2 is a vertical asymptote. If any or both limits of a function to the left-hand side or the right-hand side, or both, are infinities or do not exist in this situation of infinity, negative infinity, positive infinity, negative infinity, if at least one or both are infinities, then x equals 2 is a vertical asymptote by definition. So coming back so we can finish problem 9, it says find the equations of the vertical asymptotes. So can anyone give us equations of vertical asymptotes? X equals 6 is a vertical asymptote because at least one of the limits left and right, in this case both, are positive or negative infinity. At least one of them is infinity. What about x equals negative 7? It's a vertical asymptote. Both sides go to negative infinity. What about x equals negative 3? It's a vertical asymptote. Both sides go to infinity. X equals 0. So we have x equals negative 7, x equals negative 3, x equals 0, and x equals 6. All these are vertical asymptotes. Any questions? Now, I'd like to come back to our graphs from a few minutes ago.
I do have a question.
Yes, please.
Earlier you said L must be a real number. It's not infinity or negative infinity.
For the limit to exist. But I didn't say that the limit existed here.
Okay.
I only said that if the limits from left or right, or at least one of them, is infinity, that line represents a vertical asymptote because the limit doesn't exist
Okay.
in the sense of plus or minus infinity.
Okay.
Because if it's this situation, I cannot claim that x equals a is a vertical asymptote.
Right.
So the limit from either side is d and e. But this is not infinity and this is not negative infinity or the other way around to conclude that x equals a is a vertical asymptote. So I'm saying that the limit exists only if L is a number. But here I'm saying if the limit from the right and limit from the left, or one of them or both, are infinities, then this is a vertical asymptote. I'm not saying that the limit exists. Quite the contrary. I'm saying the limit one, or at least on one side, is infinity. Then this line is considered the vertical asymptote of a function.
So when test time comes around, is it infinity or is it D and E?
Very good. It's very good. If it's this, you cannot write d and e. You have to write infinity. If it's this, you cannot write d and e. You have to write negative infinity. But if it's this, you must write for either side.
Right.
We're talking about either side, right?
Because they're not the same.
Exactly.
Yeah.
Yeah, right. But when you, from this side will be positive infinity. From this side will be negative infinity. But if you're asked from either side, you have to say d and e. But now if you, don't forget your question. But now if you are asked, can you determine or please determine the vertical asymptote, you will say yes. This is a vertical asymptote because at least one side goes to infinity or negative infinity or both. Please.
So if the limit from the left is 2, but the limit from the right is infinity, is it still an asymptote?
Yes. Very good question. It's very possible. Thank you. Very good question. Thank you for asking that. If at least one side is infinity, it's a vertical asymptote. Of course, this cannot be a full point. Who knows? Maybe it can, the way we can define a function, there are different ways. But regardless of what happens on this side, regardless, at least one of them goes to infinity or negative infinity, this becomes a vertical asymptote. Yes, please.
But only if you say from either side.
At least one. at least one side must be infinity for this line to be considered a vertical asymptote of the function. Okay, where was I? Yes, I wanted to go back to our beautiful graphs because I want to ask you a few questions here. This is the last graph, and this was the first one that we looked at, because I have some questions. Now, yes, I accept a graph without a chart. Normally, I insist that there must be a chart, because if you just show this, you would most probably you'll not get full credit. Yes, please.
There's like any chart, like
Yeah.
okay.
That's fine. If you don't prefer this one, you prefer a different one, I'm fine. But you have to show some order there. Just this, I.
Of course.
Okay. So from this chart, though, you don't have to look at the graph to answer my questions. So I'm going to ask you find the limit as x approaches 1 from the left. You don't have to look at the graph. It's more difficult to look at the graph. Look at the chart. Limit from the left when x approaches 1 from the left. What is it? It's right here. It's right here. This is the limit, right? If I say limit from the left of 2, what will you say? Of course, it's right here. This will be more difficult to start. Okay, it's negative 2. It's right here. Limit from the right of 1. F of 1. Don't even bother with the graph. F of 1. Exactly, it's right here. F of 1 is 3. Limit from the right of 2. The limit from either side of 0. It's 0. It's right here. The left is 0. The right is 0. The limit from either side of 0 is 0. Either side of 2. As x approaches 2 from either side. Of course, it's DNE because the left is negative 2 and the right is negative 1. The limit from either side of 1. We don't care whether the function is defined at 1. It's 1. The limit from the left is 1. The limit from the right is 1. They're both the same, so the limit from either side of 1 is 1. Okay, the other one. The limit from the left of 1. Sure. The limit from the right of 1. The limit from either side of 1. You don't care about the graph. Look, it's right here. It's very clear. 3 on the left, 0 on the right. Cannot be other than D and E. The limit from the left of 3. The limit from the right of 3. And the limit from either side of 3. That's it. F of 1. If you look at the chart, you don't have to look at the graph. Does not exist. So everything matches, but this has a good, very important role. Good, very good. Okay. Now I'd like to continue with page 98. Do I still have time? Yes, I do. I like to look at some limits over there. And before we look at those limits, I'd like to discuss a very important problem or situation. Limit sine x over x as x approaches 0. What do you think this is? A wild guess. Say it again.
Does it say sine?
Yes, S-I-N. Sorry.
No, you're good.
Good. I'm happy that you're not guessing. Okay. I cannot prove this just yet. We have to wait for a theorem, and then we'll prove it. But for now, we can graph the function. So in y equals, clear whatever you have, and put in sine x make sure that you have everything in radians. I don't think I changed it from radians. No, I already have it. Okay? Divided by x. I would like to graph this function, so please go to Window. And I would like to graph this function between negative pi and pi. Negative pi and pi with a scale of pi over 4. And between negative 2 and 2. Minimum negative 2, maximum 2 with a scale of 1. So one more time, I have negative pi to pi with a scale of pi over 4. And for y minimum, negative 2, y maximum, 2. Ready? It's in the software, it's already there. So I'm going to click on graph. And here it comes. You know it's deceiving. Right.
Can you show this?
Oh. Horrible. Sorry. Okay, so let's start from scratch. So, and I'm sorry. Forgive me. So I thought I clicked on it, but I didn't. So in y equals, we enter sine x divided by x, and then we go to Window, and we punch in negative pi. Here's the negative sign, and then second and the caret.
It took me half an hour to find the negative
Right.
sign.
I'm so sorry, forgive me. So negative at the bottom, right on the 3, and then the second key, and then the caret. And that's your negative pi. Enter. And then you'll put the positive pi with second and the caret, and enter. Then it moves on to the scale, and I recommend second, which is pi, and divided by 4, and press enter. And y minimum negative 2, y maximum 2 with a scale of 1. Are we okay now? Sorry, I apologize. So now let's click on graph. Okay, here's the graph. You know that this is incorrect.
Yeah.
We all know that this is incorrect, right? This function is undefined where? Right. So do you see an open point there?
See a gap.
Kind of, sort of. But if we didn't know about that, we probably wouldn't even pay attention to it, right? So now I would like you, since you have the graph in front of you, I would like you to tell me what is this limit? 1. Thank you very much. The limit is 1. So the graph looks like this. Although the function is undefined at 0, which we don't care about. When we talk about the limit, we don't care whether the function is undefined at that point, because we know we will never be able to punch in 0, ever. So the limit is 1. And we have to remember this. Like all the other notes that we had throughout so far, since Monday, we have to remember this. Also, it happens that limit as x approaches 0 from either side of x over sine x is also 1. Okay, so I'd like to look at on page 98. And I'd like to start with problem 30. And we have limit x plus 2 over x plus 3. When x approaches negative 3 from the left. Okay, before we look at this limit, I would like to write another note. A number divided by, not 0, I should put in parentheses, 0 is also a number. Any number, but not 0, divided by 0, and put the limit in front of it, in other words, has 3 possibilities as the answer. So if I try to find the limit of a function that, in other words, is a number over 0, I have 3 possibilities: infinity, negative infinity, or DNE. In other words, also, I would write this limit will never exist. Ever. And I'll put in parentheses if you want no hope. No hope whatsoever. I didn't mean to put it in one word. My pen just fell. So it's 2 words, no hope. Now, if I have this situation, zero over 0 has hope for the limit to exist. I'm not saying it will exist. I'm saying there is hope for this limit. For 0 over 0, there is hope that the limit exists. For a number over 0, never any hope. It will be one of these 3. This may end up being 3, or negative 1/3, or whatever else you want, a number. But this one will only have these 3 possibilities. So now I can come back to my limit. I'm going to write it again. Limit of x plus 2 over x plus 3. X approaches negative 3 from the left. And now I'm going to do another thing that you will be appalled about. I'm going to plug in negative 3. And you could say, but 3 minutes ago, you just told us that you can't do that. That's true. But I have to check. By plugging in negative 3, I'm going to check and see what really happens here. I'm not going to write it, because I'm not allowed to write this, because it's not math, right? But I have to plug it in, because I have no idea what this is. So I'm going to plug in negative 3. Negative 3 plus 2 is negative 1. Negative 3 plus 3 is 0. I know now that I am facing this or this or this. If I had obtained here negative 1 over 3, I would have said the limit is negative 1/3. If I had gotten 0 over 0, I would have said, okay, I need some algebraic manipulation. See, maybe I can remove a factor. Maybe who knows what's in there. And there is hope. But I got this. Since I got this, I know I'm facing one of these 3 situations. Now I don't know which one. So here's how I verify. First of all, is from one side. From one side, it can be DNE. We had that situation a few minutes ago. It's possible. Right? Even from one side, it can be DNE. But not for a rational function. This is a function that has a trig in it, a cosine or a sine that oscillates like that. A rational function does not oscillate from left or right of a number, ever, right? It does this or this. It may have a vertical asymptote, but it does not do this, right? So from the left, it would not, in this case, it cannot be this for a rational function. So I already narrowed it down to these 2. Well, which one is it? So here's how I find. I know the answer. This must be it. What I don't know is the sign in front. Very easy to figure out. Since it's negative 3 from the left, I will imagine that I plug in negative 3.1. Because I can't plug in negative 3 because of 0 in the denominator. So negative 3.1, the top is negative, the bottom is negative. I know the sign, and I'm done. Now, if I ask you, which is not in the book, but it doesn't matter, if I'm asking you this, imagine, you have to imagine that you plug it in, you get this again, But now you know that it's -3 from the right, so you will have to plug in -2.9. The top is negative, the bottom is positive, so you know the answer. But every time you try to find, or you have to find a limit, although I said you can never plug it in, you must plug it in at least to see which category of limit you have. But I'm not allowed to write this. I wrote it down for myself. But I'm not going to say, that, well, it's -1/0, the limit. No, I can't do that. So I did this because I need to see what type of limit this is. Now, if I have the following, limit as x approaches 2 from either side, from x plus 2, x minus 2, over x minus 2, and x minus 3, I still have to plug it in. Normally, it will not be factored like this, but I chose a simple example. So I have to plug it in. When I plug in 2, this is 0 times whatever times 4, and this is 0 times -1, correct? So the situation is 0/0. I have to plug it in to see what it is. So I know that there is hope. Can it still be one of these? Yes. It can still be one of these as the final answer. But since I'm starting with 0/0, I know that there is hope. What is the factor if when I plug in 2, and this we know from pre-calculus, when I plug in 2, if I get 0, what does that mean? It means that the function has a factor of x minus 2, because only x minus 2 will make it 0. So when I plug in 2 here and I get 0, I know there must be a factor of x minus 2. When I plug in 2 and I get 0 here, I know there must be a factor of x minus 2. Since I already chose a simple example, what do I do with x minus 2? Am I allowed to? Yes, because I can never replace x by 2. I do it on the side to see what I'm facing, but I'm not allowed to plug in 2. This specifically says x approaches 2 from either side. So I'm allowed to simplify. So now the limit becomes x approaches 2 from x plus 2 over x minus 3. And what is this? What does it equal to? Yes? So the limit is -4. Very good. Back to same page. Let's look at a, yeah, why not? 36. Okay, I have 7 more minutes. 36. Limit. This is on page 98. Limit as x approaches 2 from the left of x squared minus 2x over x squared minus 4x plus 4. I have no idea what this is. I must plug in 2 on the side, somewhere in a corner. Nobody knows, but I have to do it. So when you plug in 2, what do you get at the top? Perfect. When you plug in 2, what do you get at the bottom? Good. So there is hope. It doesn't necessarily mean that the limit exists. It means only that the limit may exist. Whether in this situation, there is absolutely no hope right here. -1/0. Okay. So if when I plug in 2 and I get 0 at the top, what must happen again? There must be a factor of what? X minus 2. So let's try to figure out, or try to take it out, I should say. What will you do to the top? Very good. And what is left? Good. What about the denominator? Very good. So now, what will go away? 1 from here and 1 from here. Am I allowed to? Yes, because x is neighbor 2. So now the limit is limit as x approaches 2 from the left from x over x minus 2. Now plug it in again. What do we have? Nobody knows, but I have to do it. What is at the top? 2. What is at the bottom? Uh-oh. So, but that's okay. So now I know, since it's a rational function, it's not oscillating, I know it must be an infinity. Can anyone figure out which one?
You can just do the same thing, just plug in a value that's next to it. So it would be
Good.
negative.
What is it?
Negative.
No.
From the left side, if you take 1.
Oh, yeah, from the top is positive. He's right. From the top is positive. 2 from the left is 1.9, and the bottom is 1.9 minus 2. So it's negative indeed. Thank you. Yes, you're right. Any questions? Any questions? Say it again. Good. Excellent. That's what I wanted to hear. Okay. Let's look at a natural log, like 33. So limit x approaches 3 from, I think it's from the right, yes, of natural log x squared minus 9. Good. Now we have to remember how to graph natural log. What is the graph of natural log? How do we graph natural log x? We cannot forget this function. It's a very, very important function. And here is its graph. Good. So does this, if I ask you about this function now, just in natural log, limit as x approaches 1 from the right, what would you say? I'm sorry, I meant to write 0. 0 from the right, what will you say? Excellent. Indeed. Good. So now coming back here. This is an outer function. We're going to deal with this a lot. And this is an inner function. It's a function composition, right? This is the inner function that I evaluate first. When I get a number here, then I apply natural log to it, right? So this is the inner. This is the function I start with first. And this is the outer function. So when I still have to plug in 3, there is no escape from that. Nobody knows. I'm not going to write it down, or I'm going to write it on my scratch paper, because I'm not allowed to do that, but I have to do it. So when I plug in 3 from the right, 3 from the right, but I have to plug in 3 first, right? So 3 squared minus 9, 0, right? So when x approaches 3 from the right, this approaches 0 from the right. Right? 3 from the right is 3.1, right? So there's going to be more than 9, and 9 minus, a little bit more than 9 minus 9 will be 0 from the right, with positive numbers, in other words. So now natural log applied to 0 from the right. So when x approaches 0 from the right, so anytime we face a function composition, we always have to evaluate the inner function and then apply the outer function to that result and then identify the limit. We can never forget this, that this is the graph of natural log, and as x approaches 0 from the right of natural log, the limit is negative infinity. Okay, let's also look. I still have time? No, I don't. It's 8:24. Any questions for me?